Thank you very much. So when I went into overtime the day before yesterday, I was talking about this theorem that if you have a closed manifold, and then M emits a Lorentzian metric, if and only if the Euler characteristic of M vanishes. Okay, to sort of give you an idea of proof. And I wanted to make two remarks. First of all, the first remark is that if M is non-compact, or is non-closed, could have boundary, closed, then it always admits. If M is non-closed, then it always admits. Admits a Lorentzian metric. For the simple reason, when you remember the proof, the idea of the proof was to construct, to show that the existence of a Lorentzian metric is equivalent to the existence of a section. And if you have a non-closed manifold, the projective potential bundle always has a section. And second, if you look at this even dimension of the Zitter spaces, they do not have, does not admit compact quotients. Whereas, you know, the Zitter 3 space, what I said Tuesday, which is SL2R, with its killing form, that has compact quotients. Has compact quotients. But the classification is still open. Classification. It's a problem by Margulis. Asked by Margulis. I think nobody has so far as an idea how to completely classify. Of course, you get the unit tension bundles of hyperbolic surfaces. Okay. So, since last time I talked mostly about examples of Lorentzian manifolds, let me give you a bit of conceptual notions. What are the objects in abstract Lorentzian manifolds you usually look at? And you know that there's this dichotomy or trichotomy of vector, of the length of vectors, the energy of vectors, positive, null, or negative. And that has actually physical meaning. So if you look at a Lorentzian manifold, a Lorentzian manifold, and a tangent vector to the manifold MV is, I'm not German, is a time-like if the inner product of V with itself is negative. So if you look at, again, at this double cone picture, and inside here, that is time-like. B, it is null. You can, the literature also says light-like. If V is non-zero and the length is 0. So basically, you are on the boundary of the cones except the vertex. Yeah? A null vector is never any physically meaningful vector. C, it's space-like if it is neither of those two. So if V equals 0 or G of V is positive. Okay. So for that. And yeah. So as you might remember, so space like is not here. As you might remember from your course on relativity, the only relevant part for physics is the time-like moments. Space like what we will count as vectors. So every physically meaningful motion of a particle will be described by a curve whose tension is equal to time-like. Okay, and that suggests the following definition. And I won't give the most general one, but it's the easiest one, and it is actually enough. A C1 curve, gamma from some interval into a Lorentzian manifold is time-like. Did I have already? Oh no, I said the other way around. Stick to the plan. It's causal or time-like if the tangent vector is either null or time-like. The first case, and if it's only time, you call the curve time-like if the tangent vector is everywhere like. So basically, a causal curve can have tangent vectors inside the cones and on the boundary. But a purely time-like curve can only have tangent vectors inside the cones. And if you ask physicists, they will tell you that the motions of particles that have positive mass can only be time-like curves. To reach the boundary, to have null direction, takes infinite time. Okay. And the usual assumptions you now make to describe the geometry is that there exists a light-like vector field. Assume that there exists a x which can be chosen smooth with property that the length is everywhere negative. What is the meaning of that? That tells you in a consistent way which one of these cones you choose. That's a global assumption. For the following. This is actually not so restrictive because it's true up to holds up to a twofold cover. It's the same phenomena as when you ask about orientability. Manifold is orientable up to a twofold cover. Here it's the same thing. You're asking, if I start in this cone and continue continuously choosing vectors on a curve in this cone, then I might come back with the same direction, or I come back with the opposite direction. If I do this twice, I can come back in the same direction. So it's not a big restriction. But in physics or in relativity, you always assume that because then x is what is called the time orientation. It basically tells you what is future and what is past. Because physicists, they like to have time direction in front of them. So there's one way where time takes two. So, and if you have, so Lorentzian manifolds which have this property are called spacetimes for that reason. They're eligible models for the universe or parts of the universe if you want. And then every causal curve is, by this definition here above, is either future pointing. So you fix one x, and then it's either future pointing. That means the inner product of x with the tangent vectors is negative, or past pointing. That means the inner product of the tangent vectors of x is always positive. have this x here. Geometrically, it's supposed to point in the future direction. And the inner product of the tangent vectors of the curves being negative with x means that every causal curve, gamma, goes into this direction. The tangent vector points in the direction of this x here. That's why it's negative, because up to my sign convention, the length of the vectors here it says. Past pointing, so this is future pointing here. Past pointing, of course, is always in the direction. And then, if you have this, so why does one do this? If you look at the cones, and you know that the only curves that are actually interesting from a physics point of view to you are the time-like or causal ones, then an immediate problem becomes the question which pairs of points are actually connected by a causal and time-like curve. Basically, you want to know the reachable set of control field. And this notion I want to fix now, because that's why I define a causal curve for future pointing. So, yes, miss anything? No. So, let P and M be a point, then define, first of all, I plus of P. We can also, let me just define I plus and I minus analogously. I plus of P is those points Q and M such that there exists gamma time-like, future pointing time-like, from P to Q. So basically, in the Minkowski space, if P is this point, then is just the entire cone that points upwards. Nothing besides here. No curve, no time-like curve can travel from this point to this point. It has to have a space like tangent, so in Minkowski space. At the same, you can go with the J plus. So this would be called the chronological future. The causal future is usually denoted with J plus. It's the same thing, except one little change. You assume that this curve eta, future pointing from P to Q, and that just means it can be any causal curve, right? Including it can be the Riemann like that. So if you want to interpret this in a relativistic way that says those are the points which you can travel to, those are the points which you can at most, or at least, satisfy. Okay, and the I minus of P and J minus of P are this analog, analogously, with past pointing curves. So you could also say I minus of P are those points Q such that P lies in the chronological future of Q. You could also say something like that, but it's probably, from a point of view of symmetry, it is better to define both curves. Okay. And then remark. Since the cones, the interior, these cones in Lorentzian geometry for Lorentzian metrics have always non-empty open interior, you know that the chronological future and past of any point are always open. These are always open sets. Whereas the J plus in Minkowski space it's closed, but this is generally not true. So in general, plus minus of P is not closed, and the closure of I plus P, I plus, say, goes for I minus, is usually bigger, contains J plus, but can be bigger than J plus. And for J minus. I don't want to go into details, just let me announce that this phenomenon happens. It's pathologies. Maybe just a little argument why J plus of P is in the closure of I plus. It's somewhat instructive to see this. Well, if you have your point P down here, and you have a causal curve to a point Q in J plus of P, then you want to show that this Q is in the closure of I plus. So you need arbitrarily close, you need some time-like curve for P to a point up here. What you do is, you just take a little piece of time-like curve to the future of Q, to some point R, for example. Then you concatenate those two curves. So this is maybe gamma, and then you have a small curve eta, and then I always get this wrong. Eta past gamma is then of anyway it is causal, future point you would say. But it is an old argument by Penrose that you can perturb this curve to a third curve, let's say gamma twiddle or something, which is time-like. This has something to do with the calculus exercise, that if you have a function, if you have a straight line and you have a perpendicular line, or a little piece of line that goes in a different direction, then you get another line that has everywhere positive slope. It's sort of like this. And physics interpretation is that if you have a light signal and you wait a bit there resting at the end of the light signal, then you can actually talk. Okay, that's the idea. Geometric idea. Okay. So, and now, if I know that these I plus here, these things are open, I can actually prove to you why physicists don't look at closed space-times. It's the following theorem. If mg is Lorentzian with m closed, then there exists P and M with P it's contained in its own chronological future. So basically there exists a time machine. And that, of course, is a basic violation of any physical notation. And the proof just uses the fact that these things are open. So, but the proof by argue by contradiction. Meaning, for all P and M, we know that P is not an I plus of P. Well, we know they are open. And every point for all Q in M, there exists an R in M such that Q is in I plus of R. Simply, if you have a point, just take a past pointing light-like direction, shoot off a little geodesic, and then you have your point R. Q lies in chronological future. So everybody comes from somewhere. There's no initial point. But then the set of these chronological futures is an open cover of M. Well, M being closed implies that there's a finite subcover. So M compact means that there exists P1 to Pk such that M is in the union of those K. So, but then for all I, there exists a J such that Pi is in the, or P, yeah, for all J there exists a I such that Pj is in the future of Pi. But then you only have finitely many possibilities. So you start with one. So you start with P1, then there exists a P, I don't know, Pi here. Such a P1 lies in the future of that thing. But that Pi must be in the future of some Pi2, and so on. But you only have finitely many possibilities. So at some point you go with so. At some point. The indices repeat. And then, of course, then you can concatenate these curves and you get a closed curve. Concatenation of timeline curves yields timeline curves, but especially it yields a closed timeline. So one of those PIs is in its chronological future. Spacetimes or Lorentzian manifolds with this property are called not chronological because there is no well-defined clock on this. If you have a clock and it starts ticking, it comes back to itself. At some point, the indices repeat. Closed Lorentzian so this is maybe implies G is not chronological. So chronologically means that there is no closed time. So why do I tell you this for, not just for pure sports, but to introduce you to certain assumptions which come up everywhere in Lorentzian geometry, which are usually made in order to get some meaningful geometry out of this. And this chronological, it's a property that the compact spacetime is not chronological, has to be strengthened a bit more, because as I told you, the existence of things talking to themselves is not just confined to time-like curves that you can travel back to yourself, but also that you can communicate with yourself, because then you can tell yourself the lottery numbers of next week. This is not good. So one usually strengthens this assumption here on spacetimes to the non-existence of closed causal curves, not just time-like curves. So spacetime mg is causal if there does not exist a causal loop. That's so basically that's the most basic assumption you would have to make to be meaningful to describe. And B, in order to have, for example, existence of geodesics, which I will talk about next, is the so-called global hyperbolicity, a space-time G is globally hyperbolic. If it is causal and the sets J plus of P intersected with J minus of Q of a second point is always compact. I don't want to comment too much. I mean, this is obvious from physics reasoning. Why this? The other condition in global hyperbolicity. Let me put it this way. First of all, global hyperbolicity is the most important assumption on Lorentzian manifold. They appear throughout. As the name suggests, the condition comes from wave equations and basically guarantees that solutions of wave equations on spacetimes exist and are unique. And there's no, exists is this causality, and uniqueness is this, or preservation of energy comes from this condition. But I don't want to mention that too much. I want to rather point towards geometric meaning of this condition. I want to say anything else. Not so far. Maybe what I can, as a preview, say global hyperbolicity for Lorentzian manifold is something similar to completeness of Riemannian manifolds. Even though these spacetimes, globally hyperbolic spacetimes, don't need to be geodesically complete. This analogy rather extends to the existence of geodesics. It's minimizing geodesics. Okay. Alright, get back to the examples. So all examples I've shown you on Tuesday.
Wait, erst. So das ist immediately implied that you have between points there the minimizing
Yes. You will come to that.
You compact set it, you just minimize it.
Exactly. It's a bit more because I will come to that.
Okay.
I will make a mark and then I will. Okay. So all examples I've shown you before, except the Mesmer spacetime. Except the Mesmer spacetime are globally hyperbolic. Especially all spacetimes that are usually considered in GR are globally hyperbolic, except for some pathological examples. And picture I already drew on Tuesday shows you that the Misner space-time, even though it's non-compact, is not chronological. There were closed time-back curves in that. Okay. And now to first I have to define to actually what the length of a causal curve is. So, for an absolutely continuous curve, in your space-time, you can define the length with respect to your Lorentzian metric simply as the integral over I of the square root, and now you have to take the absolute value, since this might not be a positive number, of the length of tangent vectors. If it's absolutely continuous, this is well defined almost everywhere, so you can write this down. This will be written if I is compact, for example. The problem here is, if you write it like that, for curves, so fix P not Q, works for P equal Q as well, but that's not an interesting case. In M2 points, then LG is not bounded from below, bounded away from zero, bounded away from zero on paths between P and Q. Actually, what you get, you can always construct the path of length 0 between any points. Paths between P and Q. The picture is, if you have P and Q, okay, I assume here silently that M is always connected, so you have a path, some path, eta, arbitrary, that's an arbitrary path. What you can do, you can zigzag with light-like curves, with null curves, following this path. Of course, this part will be future pointing, and this part will be past pointing, future pointing, past pointing, future pointing, past pointing, but you can get it from anywhere to anywhere. These are null pieces. Since I made absolutely no restriction on how this curve what geometric properties this curves have, I get this curve gamma. So gamma is actually Lipschitz, but it's especially absolutely continuous from P to Q, and the length of gamma is 0. I mean, of course, this is always a non-negative real number. So extrematizing curves as such in Lorentzian manifold by bounding it from below is pointless.
If your original path was timeline, you can also do it by OSC.
Exactly. That's what I'm trying to motivate, why you restrict it in that way. And of course, as you know from Riemannian geometry, this thing is also not bounded from above. There's no pointless to talk about bounding from above, but that in essence tells you, so the way out here, escape. This problem is restrict to Q in J plus of P and gamma future pointing curves. Then this starts making sense. Then you cannot do this anymore. what then follows so let me just formulate the theorem and then discuss it. Then you have the Ave-Seifert Theorem, which tells you if you are in a globally hyperbolic manifold and Q is in the chronological future of P, then there exists a future pointing curve from P to Q, that maximizes the length, of future pointing curves between P and Q. That's the analogy with minimizing geodesics in many geometry. Yeah?
Could you say again the definition of the J plus? Right?
J plus? The J plus is simply that set of points which are reachable from P by a future pointing path. Here you have to maximize length because if I write it like that, the function, so the function square root of g, absolute value gvv, v is mapped to this, is concave on the future pointing vectors, is fiber-wise concave. Fiber-wise concave on the future pointing vectors. Did not define that, but it's obvious. Yeah? Those vectors are inner product, negative inner product with this vector field. Why it's concave? Well, if you it's a one homogeneous function whose cross section looks like this. Well, let me put it another way. If you look at it in 2 dimensions already, then you have the function. So let's put it. Let's say you have 2 coordinates, x and y. The inner product in 2 dimensions is, let's say, x squared minus y squared. Take the square root of that thing. Look at restricted to the set of points such that y is bigger or equal than the absolute value of x, which is just really not common. This thing.
Take absolute value. You need to take absolute value.
Sorry, yes. Yes, then I should, yeah. This is a concave function. If you take the cross section, if you set x equal to 1, then it looks like this. Y and this is 4. X equal to 1. And if you have a concave Lagrangian, you have to maximize. Whereas in the convex case, you minimize. The proof is instructive, even if you know the Riemannian proof. Maybe a remark. I want to say a few things. general, this is not true for non-globally hyperbolic spacetimes. For example, compact ones. If you have a closed spacetime, then of course you have time-like loops, and then the length, the maximal length of time-like curves from that point to itself will be infinity, because you can just iterate. So that's why you assume global hyperbolicity here. And for dimension of M, at least 3, dimension 2 is a bit special, yeah, because there the Lorentzian signature is spin signature. No such statement on curves, no such statement for curves, for space-like curves exists. Even locally, you can always make the curves, the length of space-like curves from the points that are close by, as long as you like. It has something to do with the fact that the index for a dimension at least 3, the co-index is at least 2, it's bigger than 1. There's a student of Lawson, I think, who wrote in the 80s a thesis saying that if you have a pseudo-Riemannian manifold, it means that you have an inner product of some arbitrary constant index, let's say k, then the only chances for something meaningful in this maximization problem is for geometric objects of dimension index or co-index. So in Lorentzian manifolds, the only thing you can meaningfully maximize are causal curves or space-like hypersurfaces. Everything else just doesn't make sense. Okay, and I wanted to give you the road signs of the proof. Because especially the first point is something you probably do not see as such in Riemannian geometry, which is a simple application of Acela-Ascoli. Or since I still work with Alberto, I should say Ascoli-Acela. Italians make quite a point of this. So what does it say? When I say Ascoli-Acela theorem, then I always have to start with some metric structure. And that's usually what you do in Lorentzian geometry. I mean, if you want to measure something, or put it another way, to an arbitrarily given Lorentzian metric, there is no canonically associated metric structure to it. That's one of the big issues in Lorentzian geometry, where many things don't work. But you can always, of course, choose a background metric arbitrarily just to say I want to measure some distances. So we let H be a complete Riemannian metric on a space-time mg. As H does not need to have anything to do with it. It's just there to say something about metric structures. And gamma n is sequence, and I want to make them be defined on their entire real line. Sequence of H arc length parameterized writing. Miniaturized future pointing curves. I did not say that explicitly, but by my definition of causal curves, they are always regular. So you can always parameterize them with respect to Riemannian measure. Okay. If the sequence of values at 0 is bounded in M, basically metric space reduced by H. There exists by Acela Ascoli. There exists, of course, a subsequence gamma and K, K and N, converging on compact subsets, converging uniformly on compact subsets. Subsets, and now comes the difference that's not so obvious. Compact subsets to a future pointing curve gamma, the real line, to N. Here I'm slightly cheating because this curve does not need to be C1, of course. You can have a sequence of C1 curves that do not converge to a C1 curve. But I can easily extend the definition I gave you for causal curves from the C1 case to Lipschitz curves by saying that the tangent vector that almost everywhere exists is non-zero and you have to work a little bit more because you have to avoid that you create benches like this, because here the curve is not differentiable, but everywhere else tangent vector is causal, so you have to avoid this. Didn't want to talk much about this, that's why. But here this appears natural. Okay. That is the limit curve lemma. That's the one point. That basically tells you. So what is the usual strategy for these theorems? First you show that there's an upper bound, and then you take a maximizing sequence. Then you need to, for this thing to converge, you need a second. So the second part is the upper semi-conductivity. And that simply says if gamma n converges uniformly to gamma, then the lim sup of lengths gamma n is smaller or equal to these should be future pointing curves. Now, what proof goes, of course, I can simply say words. If you have this global hyperbolicity, that where you know that the set where you have 2 points, P and Q, and you know that the past of Q and the intersected with the future of P is compact. You look at all those curves, connecting them and all future pointing causal curves. Then the limit curve lemma says that any sequence in here, which you can extend to make it define an entire real line, has a converging subsequence, which then uniformly converges to a causal curve. And if this is a maximizing sequence of the length, then of course the limit will be maximizing. In Riemannian geometry, you don't need that, because there, to minimize, you know that it already stays in the bubble set. So, what I did not say so far, any maximizing curve is a pre-geodesic. Meaning, is a geodesic up to parameterization. It actually calls a geodesic. Calls it pre-geodesic in that case. Locally, you can make a similar argument with the exponential function as in the Romanian case, that you show that geodesics are locally minimizing. You can do the same thing here with the causal geodesics in the neighborhood. But otherwise, how to see that they are geodesics? You just calculate the Lagrange equation to length function when you see the series function to parameterization. Geodesic equation. That is maybe the first remark. And the second remark is every point in a Lorentzian manifold, every point in a Lorentzian manifold has a globally hyperbolic neighborhood. Meaning, if I restrict the Lorentzian metric to that neighborhood, then it becomes a globally hyperbolic space. So you could, in some way, compare global hyperbolicity also to convexity. Every point in a Riemannian manifold has a convex neighborhood. This is per se also true in the Lorentzian case, but in terms of this minimization property, convexity is here rather replaced by corollary. Before I was talking about this control theoretic point of view about the reachability of sets. So here now, if mg is globally hyperbolic, then you know that the image of the exponent under the exponential map based at a point P of those V in the tangent space to P such that V is future pointing time-like is exactly I plus of P. Because to every point in here I get a maximizing geodesic. That is since there's a time-like curve, the maximal length of curves between P and that point in here has to be positive. So this maximizing geodesic will be time-like, so it will be the image of some time-like vector. The same goes, of course, for the future pointing causal. This time with J plus, because you have to take into account the lightning points as well. So, if you want to say this in terms of physicists would say, every point you can reach by free falling observer, and every point here you can reach by either a free falling observer or by a light signal. Global hyperbolicity. and maybe after 5 minutes, then I can give you a definition of the distance function. So we can talk about geodesics and Morse theory tomorrow. So the function is actually d, g usually. It goes from m times m to r union infinity, defined as take a pair of points, map them to the supremum over lengths of causal curves from gamma future pointing from P to Q. So you take basically this maximum length of the causal globally hyperbolic case from a causally related point, extend this to the entire manifold by saying that the supremum over the empty set is 0, which is maybe not the universal convention. Works here. This function is called the Lorentzian distance, and it actually only makes sense for the globally hyperbolic case, even though it is defined for everyone. For example, in the compact case, there will be quite a large set of points where this function is infinity. But in the globally hyperbolic case, it is always real valued and actually continuous, even though it has large parts where it's 0.
So,
This is non-symmetric, yes, exactly. It is called the distance, even though it's not a distance. So it's not positive definite, so you have points that are different and their Lorentzian distance is 0. In this convention, I sometimes use a different convention because of difference. That is not the case, it's not symmetric, and the triangle inequality is a reverse triangle.
not much reason to call it.
No, I think this is psychological data. It's purely psychological. And the last remark for today. I talked about the length. And if you look in the physics books, the length in relativity is actually the energy. So I'm not making too much error here when we talk about later about Morse theory. The Lorentzian length function is the relativistic energy of a falling particle, of a moving particle. But you could argue that you should really look at the energy of curves as you would do in Riemannian geometry. So the energy, in this case, not L, but E, of a curve gamma being 1/2 integral over G gamma dot dt has no such maximization behavior. Even in the has no such maximization behavior. Even in the globally hyperbolic case. It is unbounded in both directions, which you can actually see. You unbound it, you can either slow a curve to make it very slow, to make the energy almost disappear, or you can make it very fast to make the energy explode. So there's no meaningful way to bound the energy, even for causally related points in causal curves. And the interesting point here, which that's why I always tell this like the geometers, is that the index of every geodesic the index and the co-index. Don't argue with minus the energy. Of every geodesic is infinite. So it looks in that respect, it looks like the Hamiltonian natural function. Even though I've never found a reason why that should be, or if there is a meaningful relation. Okay. And the second one I already said. Yeah. So, the length of G is the relativistic energy. So it makes much more sense to, even from a more theoretic point, to look at the length, not only for that reason, also for the intrinsic reasons that come from physics, intrinsic interpretation of Lorentzian geometry as activity to look at. Okay, and I'm exactly.
So let's take our speech. Any questions? Not today.
You already done?